Okay, a couple of sections ago we talked about common logarithms. Common logarithms, and were special logarithms where they had a base 10. And remember that if we had a common logarithm, there's a special way that we could write it. Well, similar is true to what we're going to talk about today with natural logarithms. Now, any positive number, like it says here, except for 1, can be used as the base of a logarithm. And remember from the previous chapter, we talked about the number e. I guess we learned about that in 9.3. That we use in logarithms as well, because e is a number. I mean, pi is a number, so we could use pi as a base for a logarithm. So if that's true, then we could use e as a base for a logarithm. Anytime we use a base e, we call that a natural logarithm. Now, like I mentioned earlier, if we have a common logarithm, that means it has a base 10. A shorthand way to write it is just log of x. So anytime you see log of x, you automatically know that the base you're dealing with is 10, even though you don't see it. You need to be just as familiar with the natural log of x. We use the ln to represent the natural log. So anytime you see that, you need to recognize the fact that that's the same as log base e. So again, the key here is to know that anytime you see natural log or ln, you're dealing with the base e. And you have a button on your calculator that says ln. They'll usually use a capital letter L and a capital letter N. And we'll be looking at that here in a minute. From this next box, as far as what you need to make sure you understand, is the fact that if you have something written in exponential form, like this, with a base e, if we want to write that in logarithm form, it would be log base e, which remember is the same as the natural log of your value, which is m, equals your exponent, which is n. Okay, so let's talk about how we would do some of these. First off, let's do some of these without a calculator, what I have written over here on the right, the natural log of 1, the natural log of e, and the natural log of e cubed. These would be all problems that you might see on a test or a quiz where you have to do it without a calculator. So the key thing to remember is that the natural log is the same as the log of base e. So for this one, the natural log of 1 is the same as log base e of 1. In other words, we're trying to figure out what exponent we would apply to e that would give me 1 as my answer. So e to what exponent would give me 1? Well, anything raised to the 0 power would be 1, so my answer would be 0. Let's look at the next one, the natural log of e. Remember, natural log is the same as log base e. So we're trying to figure out what exponent would I apply to e that would give me e. Well, what exponent would I apply to e for it to stay the same would be 1. E to the first power stays in e. So the natural log of e cubed would be what exponent would apply to e, because remember it's log base e. What exponent would I apply to e that would give me e cubed? Well, it would be 3. Now again, some of these we're just going to type in on a calculator. Now it's important to know how to round, because I know you can just plug things in a calculator. I mean, any kid can do that. But you want to make sure that you know how to round. So when it says round to the nearest thousandth, if you have your answer and you don't round to the nearest thousandth, you will lose points on your quiz or on your test. So here's a little trick if I haven't told you already. If you don't know how many places after the decimal the thousandth place is, just think of 1,000 has 3 zeros, so we're looking at 3 numbers past the decimal. So let's go to your calculators and let's see where that natural log button is. So over here on your CAS calculator is where we found the log button. So the natural log, which makes sense, if e to the x power, if natural log is the base e, makes sense that we put the two of those together. So we're going to do the natural log of 100. Whoops. And when you do that and hit enter, we get this large number. Remember, we're trying to round to 3 numbers after the decimal. So look after the 5 is a 1, so I don't need to round. So it's going to stay 4.605. That would be your answer. So with these other ones, that's all you do. Just plug them in on your calculator and get your answer. So since that's all you're doing, we're just going to do the one example. Let's look at the next one. Here it says, according to the Beer-Lambert law, if you shine a 10 lumen light into a lake, the light intensity I in lumens. So again, lumens is how we measure that's the unit that we use to measure light intensity. So the intensity at a depth of d feet underwater is given by this equation, where k is a measure of the light absorbance of the water. For a lake where k is 34, at what depth is the light intensity 6 lumens? So they give us their value for I, they give us their value for k, so we just have to plug these in to find the depth where these numbers would work out. So just a matter of, again, plugging this in your calculator. So the depth would equal the opposite of k, so negative 34, times the natural log of your light intensity, which is 6 lumens, divided by 10. So again, we'll just go to our calculator. So it's going to be negative 34. Oops. So negative 34 times the natural log. So control the e to the x power is where we find the natural log. Notice how it already sets up parentheses. If you're using a scientific calculator, sometimes they don't always give you the parentheses. So make sure that if they don't give you the parentheses, that you type in the parentheses, because you want to take 6 divided by 10. Close off our parentheses and hit enter. And sure enough, we get 17.37, or you could say 17.4 feet. So very simple as far as that example is concerned, just plugging numbers into the correct spot. Same thing with example 2. C represents the velocity of the exhaust. R represents the ratio of the mass of a rocket with its fuel to its mass without fuel. And so they give us the ratio is 19, so that would be your R. They give us that the velocity of such a rocket might be about 2.4 meters per second, so that's your value for C. We plug those in to your equation, plug it into your calculator, you get your answer. So those are the easier ones. Let's look at something that's a little bit more challenging. Now, for some reason, when I transfer this to a PDF file, it got kind of blurry here, so if you can't read that, this is the equation that we're using in this formula. It says that O sub 1 and O sub 2 be the temperatures of a cooling object before and after taken t minutes to cool. Let's stop for a second. So O sub 1 represents the temperature before it started to cool. O sub 2 would represent the temperature after a certain amount of time of cooling. S sub 1 and S sub 2 is going to be the temperatures of the surrounding environment before and after those t minutes. So in other words, it's the room temperature. Newton's law of cooling gives us this equation. The constant of variation, which is K in this case, depends on a number of things. It depends on the temperature scale if you're using degrees Celsius or degrees Fahrenheit. It depends on the type of container the object is being cooked in, so whether you're using maybe a plastic container or a saucepan or a pot. It depends on the altitude, so if you're cooking up in the mountains versus how you compare to sea level here, and other environmental conditions. So after bringing water to a boil, which is 212 degrees Fahrenheit, Laura let her soup cool for 15 minutes to 140 degrees Fahrenheit. After letting her soup boil. But use the data to find the value of K if Laura is making her soup in an 80-degree Fahrenheit kitchen. Okay, first we need to identify some things to make this easier for us. So we know our O sub 1 is the temperature when we first started, so she brought it to a boil, so that's 212 degrees Fahrenheit. Then she lets it cool for 15 minutes down to 140 degrees. And her time is 15. The S sub 1 and S sub 2 here are going to be the same because we're assuming that when it says that she's making her soup in a 80-degree Fahrenheit kitchen, we're going to assume that it's going to be a constant temperature there. So we're just going to plug these numbers into our equation here, and our goal is to figure out the value of K. So it's going to be the temperature, which is 15, equals the K times the natural log of O sub 2 minus S sub 2, so 140 minus 80, all over O sub 1 minus S sub 1. So it's going to be 212 minus 80. Now the natural log of this giant fraction here is going to be a number, so let's simplify that. So it's going to be 15 equals K times the natural log. 140 minus 80 is going to give me 60. And 212 minus 80, that would be 132. So if you type that in on your calculator, you're going to get, well, what we're going to type in on our calculator is we're going to type in the natural log of 60 divided by 132. So the natural log of 60 divided by 132 gives us negative, we'll round this to negative 0.788. So it's going to be 15 equals k times negative 0.788. And now we just need to figure out what k is, so I'm going to divide both sides by negative 0.788, and when you do that, you get approximately negative 19 as your answer. Now that's our value for k. Now remember, k, like they said here, depends on a number of things. It depends on the temperature, type of container, all sorts of different conditions. So as long as she continues to cook in the same kitchen with the same pot, everything's going to be fine, and we can use that value for k. And that's what's happening in part B here. It says, suppose Laura heats a pot of vegetable soup to boiling and lets it cool 15 minutes before serving. What is the serving temperature of the soup if the kitchen is 70 degrees Fahrenheit? So we're assuming that the constant of variation is going to remain the same here, that she's using the same pot and all the environmental conditions are the same. The only thing that's different here is the room temperature. And that's okay. So our time is still 15 minutes. Your value for k is what we just found of negative 19 times the natural log. But this time we're trying to figure out the cooled temperature after 15 minutes. So the O sub 2 is what we're trying to find here. So our room temperature is 70 degrees though, so it's going to be x minus 70. She started out at boiling, so that would be 212 minus 70. Now this time, the variable that I'm looking for is embedded after this natural logarithm. That's what I'm trying to find. So this one's a little trickier because I can't just take the natural log of the items in the parentheses. So in other words, I'm going to have to rewrite this to put this in exponential form. So remember, if you get to a point where you're stuck and you don't know what to do, always go back to rewriting it in exponential form. But in order to do that, I need to get the logarithm, in this case the natural log of it, by itself. So I'm going to divide both sides by negative 19. So when I do that, I'm going to get negative 0.789 equals a natural log of x minus 70. We can simplify 212 minus 70. That's going to be 142. But again, like I said earlier, we're stuck now. We don't know what to do, so we're going to put this in exponential form. Remember, natural log is the same as log base e, so if at the beginning here, if that helps you to rewrite that, you can do that. There's no rule saying you can't. But to put this in exponential form, remember the e is going to be your base. We're going to drag that over. What a logarithm is equal to is your exponent, so it's going to be e to the negative 0.789 equals x minus 70 divided by 142. Now what's going to happen is I'm going to multiply, because I want to get the x by itself, so I'm going to multiply both sides by 142. So to see on your calculator how we would do that, so again it's going to be 142 times e. Oops, you don't have to do control this time, just do e. Whoops. And our exponent's negative 0.789. And we get 64.5. So it's going to be on the left here, this is 64.5 equals x minus 70. If I add 70 to both sides, that'll give me my answer. So my answer would be x equals, so the cooled off temperature is 134.5, or you could even round to 135 degrees Fahrenheit. So it takes a little bit more work. Let's try a different one. Let's look at this one. It says, under certain geographic conditions, the wind velocity v at a height h, that's what this is, centimeters above the ground is given by this formula. V equals k times the natural log of h divided by h sub 0, where k is a positive constant that depends on air density, average wind velocity, and other factors. H sub 0 is a roughness value, depending on the roughness of the vegetation on the ground. Suppose h sub 0 is 0.7 centimeters, a value that applies to a lawn 3 centimeters high. If the wind velocity is 435 centimeters per second, what is the value of k? So we're going to figure out what k is here. So we know that the velocity is 435. Our h is going to be 3 centimeters, and our h sub 0 is 0.7. So to do this on your calculator, you would take the natural log of 3 divided by 0.7, and when you do that on your calculators, you end up getting 1.455. So it's going to be 435 equals k times 1.455. Divide both sides by 1.455, and when you do that, you get approximately 298.9. Or let's just round it to 299 is our value for k. So it says at what height above the ground is the wind velocity 1,500 centimeters per second. So now I want to figure out what h is. So I'm going to use that same equation. So it's going to be the velocity, which is 1,500 centimeters per second, equals k, which we just found to be 299. Whoops. Times the natural log. We're trying to figure out what the height above the ground would be, so that's our variable. You can use x or h, and it's still going to be 0.7. So since our variable is inside the natural log here, I'm going to have to change this to be an exponential form. But first I need to get the natural log by itself, so I'm going to divide by 299, which will be just under, or just a little bit over 5. So let's see, 1,500 divided by 299 is going to be 5.02. So again, put this in exponential form, so it's going to be e, because remember the logarithm, or natural logarithm has a log base e, the 5.02 power equals h divided by 0.7. If you multiply both sides by 0.7, you'll find h. And when you do that, you get approximately 105.6 centimeters. So not all of them are as tricky as the previous one that we did. The one we're dealing with the cooling temperature of the soup. So this one was a little bit easier. But hopefully you understand now about natural logarithms. The key idea here is that a natural logarithm is basically just a logarithm using a base of e. So with that, good luck on your assignment.